Have you ever stopped to think about how the tiny, almost silent electrical signal from a microphone can totally fill a stadium with sound? Or, how a super faint radio wave from miles away turns into crystal clear music in your car? Well, it's basically a kind of electronic magic, and today we are going to pull back the curtain and see exactly how it all works. Right, this is the core question, isn't it? In the world of electronics, we're almost always dealing with signals that are just incredibly weak. To make them useful, to get them to do anything really, from driving a speaker to crunching data, we've got to find a way to make them bigger, stronger, and louder, all without messing them up.
And the answer to our big question actually comes from this amazing foundational document for electronics students put out by the Malaysian Ministry of Education. It breaks down the one key component that makes all of this possible, a tiny little device that, no exaggeration, absolutely changed the world.
And here it is, the transistor. This little thing is the undisputed hero of all modern electronics. Now, it has a few different jobs, but its most powerful role, by far, is as an amplifier. It is the engine that takes that tiny whisper of a signal and cranks it up into a roar. So how does it actually do that?
Now, you can actually wire up a transistor in a few different ways. But if you want maximum amplification, the biggest possible roar, one setup really stands out from the rest. And that's the common emitter configuration. This is the absolute workhorse of amplifier circuits, and it's the one we're going to build and understand step by step.
Okay, so let's get our hands dirty, electronically speaking, of course. We're going to put this amplifier together piece by piece, right here, to see exactly how it's built to pull off this amazing feat of amplification.
All right, here's the basic layout. A transistor has three connections, or legs: the base, the collector, and the emitter. In our setup, the weak input signal goes into the base. We then take our new, strong, amplified signal out of the collector. So what about the emitter? Well, it's connected to both the input and the output, making it the common point for the whole circuit. Makes sense, right? But a transistor just sitting there on its own is kind of like a sleeping giant. To wake it up, we have to apply some very specific DC voltages. This is a process called biasing. You can think of it like turning the ignition key in a car. These voltages don't actually amplify anything on their own, but they get the transistor all warmed up and into its active, ready-to-amplify state. Okay, now we're looking at a real, practical circuit. We've added two absolutely crucial resistors. That base resistor, RB, it's like a bouncer at a club door, carefully limiting the input current to make sure the transistor doesn't get overwhelmed. Meanwhile, that collector resistor, RC, that's where the real work gets done. It is essential for turning the amplified current into the amplified voltage signal that we need at the output. So, with our circuit all set up, we can finally focus on its whole purpose in life, amplification, or as engineers like to call it, gain. This is where we get to see exactly how a tiny little input creates a massive output.
The best way to wrap your head around this is to think of a water faucet. The tiny input current going into the base, that's like the little twist you give the handle. It takes almost no effort at all, but that tiny action controls a much, much larger flow, the huge gush of water coming out of the spout. That's our collector current, a small action controlling a huge result.
And this amplifying power, it actually has a name. It's called beta. It's really just a simple ratio that tells you how many times bigger the output current is compared to the input current you started with. So if a transistor has a beta of, say, 100, it means for every one little bit of current you put into the base, you get 100 bits of current out of the collector.
Let's make this totally real. The source material gives us a perfect example. An input current of just 50 microamps, that is tiny, at the base, results in an output current of 5 milliamps at the collector. That's 5,000 microamps. You do the math, and what do you get? A current gain, a beta, of exactly 100. That is amplification, right there in the numbers.
So our signal is now 100 times stronger. Awesome! But something really strange and super important happens to that signal as it passes through the amplifier. It actually gets flipped completely upside down.
And wow, this picture says it all. The input signal is this nice, smooth wave. The output is way bigger, for sure, but look closely. It's an exact mirror image. When the input wave goes up, the output wave goes down. This is what's known as a 180-degree phase inversion.
So why on earth does it flip? Well, it's this really cool chain reaction. First, the input voltage goes up. That lets more current into the base. Then, that unleashes a much bigger current at the collector. Now remember that collector resistor, RC? As more current rushes through it, the amount of voltage that gets used up or dropped across it goes up. And since we measure our output after that resistor, a bigger drop there means the final output voltage we actually see has to go down. It's just a beautiful piece of electrical logic.
So we have high gain and we have an inverted signal. These are just two parts of this common emitter amplifier's really distinct personality. So let's just quickly run through its key characteristics.
Now, this is a crucial point: how it plays with other circuits. It has a low resistance to the input signal, which basically means it's a really good listener. It doesn't struggle to accept a weak signal. But it presents a high resistance at its output, which makes it a very strong source for whatever the next stage in the circuit is. This combination is exactly what makes it so great at connecting different parts of an electronic system together.
And here's the whole shebang, all in one place. This table from the source material just gives us the complete picture. You've got low input resistance, high output resistance. You've got high gain for current, voltage, and power. And of course, that signature 180-degree phase shift. This is the complete personality profile of our amazing little amplifier.
Okay, we've gone from a simple question all the way to a complete amplifier. Let's boil it all down to the three key things you really need to remember from all this. So, here are the three big ideas. First, the core principle. That tiny twist on the faucet, a small base current, controls a massive flow of collector current. Second, the result. This whole setup gives you high gain across the board, making signals way, way stronger. And third, the quirk. The output is always a mirror image of the input, flipped a perfect 180 degrees. So, we've seen how just a single transistor can take a whisper and start to turn it into a roar. Just think about this for a second. The processor in the very device you're watching this on right now, it contains not one, but billions of them. And that really leaves us with a final thought. If just one can do all this, what are the incredible, mind-blowing possibilities when you have billions of them all working together?